Okay, so today we're going to talk about limits, right? And in particular, a special type of limit that we're going to look at, right? Now, first one here is, well, previously we had a method for evaluating, in particular, rational functions that look like this, all right? And we said, all right, well, we'll set out to try and factor. Factor and cancel was really what the goal here was, right? We had something like this here. So we're able to reduce here, and then we're at a form where we say, all right, now let me plug this in, and we get -5 here. Excuse me. All right, and that was a way to evaluate this, right? Now, when we had something, we also, in first semester calculus, this was a very important limit that showed up, and we developed an algebraic, or excuse me, not algebraic, a geometric way through the unit circle and making some constructions, and we were able to prove that this was the case. All right, but this isn't always going to be available to us, right? Some kind of geometric option. In general, some of these limits can be very hard to prove. Right, like for example here, let's take a look at this here, where we have as x approaches 1. Now, one thing to notice here, so we're going to be looking at particular types of limits, right? And if we notice here, if we take the limit as x approaches 1 of ln of x, well, that value is 0, right? The natural log, or the log of any log of 1 is 0. And then in particular here, the limit, excuse me, limit as x approaches 1 of x minus 1, so plugging in 1, we also get 0. Okay, so we could see that both of these quantities, the natural log and the x minus 1, they're both approaching 0, right? So we're getting really small. Right, now this idea is, or this type of limit, I should say, is what's called the indeterminate form. Right, so, and that's exactly what that means, indeterminate, and the fact that I don't know what that value is going to be. All right, maybe it's 0, maybe it's undefined, maybe it's something else. All right, I have yet to determine what the result is going to be. So a really powerful theorem here is L'Hopital's rule. So L'Hopital's rule is going to apply. So there's very specific instances where it applies. Now the first one being is when we have a ratio of two functions, f of x over g of x, right? And this is going to apply for two particular instances, right? If the limit as x approaches a of f of x is equal to the limit as x approaches a of g of x is equal to 0, right? So they're both tending to 0. Or the limit as x approaches a of f of x is equal to the limit as x approaches a of g of x is equal to infinity. Now for this one, the infinity one, it's not going to matter whether it's positive or negative, because really that just comes down to multiplying in a some kind of constant. So what we have here is these two quantities where L'Hopital's rule is going to apply. Now L'Hopital's rule states that, and I'll write it here, the limit as x approaches a over f of x and g of x is equal to the limit as x approaches a of f prime of x over g prime of x, which is a very surprising result, I think, and one that is also very fortuitous, really helpful, right? The implications of it are really widespread, in that now I can evaluate such a limit by simply taking the derivative of the numerator and the denominator, right? Now keep that in mind, right? I am not applying the quotient rule. I'm just simply thinking of them as two separate functions and taking the derivative of each one of those individually, right? And now we could see, right? Let's go just to show how this works to some previously established limits. And then we'll go into the logarithm one that I introduce and apply it there, right? So something like this, right? So you establish both going to 0, right? I plug in the numerator a -2, I get 0, okay? And then down here, I also get 0. So it is indeterminate. So L'Hopital's rule says take the derivative of the numerator, and that lands me at 2x minus 1 over 1, right? And now I can just plug in, right? Now, one thing to keep in mind is that the new limit is not indeterminate form, right? So we could simply here, this is an even easier limit. I don't need to do much work other than plug in -2. And we get -5. All right, which confirms our result up there, right? Okay, so that is an application here of L'Hopital's rule, right? So now the limit as x goes to 0 of sine of x over x. Again, both quantities approaching 0. So applying L'Hopital's rule, we get cosine x over 1, right? And again, right, no longer indeterminate, right? 1 is constant, so we're just plug it into cosine, and cosine of 0 is indeed 1. All right, so we see now we have a better approach, a more systematic here, where we just need to find the derivative. So now we can go to the next one here, the limit as x approaches 1, natural log of x over x minus 1. Again, right, I can't stress this enough. Make sure that it is, in fact, the indeterminate form, okay? If it is not the indeterminate form, then the L'Hopital's rule does not apply and it will not lead to a correct result, okay? So once we've identified here that both of these quantities are indeed going to 0, so now I'll take the derivative here, and that's 1. And then that all simply converges to the value of 1 by just simply plugging that in. Okay? All right. So that is how we apply L'Hopital's rule when it is for the indeterminate form. Right? In later videos, we'll look at other forms that aren't necessarily 0 over 0 or infinity over 0, or excuse me, infinity over infinity, but we can manipulate them so that we can, in fact, use L'Hopital's rule.